Hi friends, welcome to follow up. Let's have a look at problem 1802, maximum value at a given index in a bounded array. This problem actually is a standard application of binary search. So here we are going to explain the thought process. First, we are given three positive integers, n, integer, and max sum, and we want to construct an array nums. So here it emphasizes that it's zero indexed. So we want the array to be satisfying the following conditions. First, the length is n, and at the index I, the not at index. So for at every index, so the number nums I is positive, and the neighboring element has a difference less than or equal to 1 in absolute value. So, and also the sum of all the elements does not exceed max sum. So also we want to maximize the element at the given index, right? So we want to return the nums index of the constructed array. So here are two examples. So in the first example, so at index 2, here we have 2, right? So here the array is 1, 2, 2, 1. So the sum is 6, is equal to the given max sum. This is a valid one, and the return value is 2. So if we set this value to be 2, actually for the element at index 1, we can set it to be 1. This is also good. So this is the first example. For the second example, the output is 3. So you can actually try to construct one valid array. So now the constraints for the problem are the following. First, n is bounded below by 1 and bounded by the max sum, and then bounded by 10 to the power 9. And the index is inbound, so this is just for consistency. So with that said, we are ready to explain the idea. So here actually, if we have practiced a lot of problems on binary search, actually once you see this problem statement, basically you can have a feeling on how to use binary search here. So here first we are going to transform the problem to be the following. So we want to find max key such that the length n array at index give here, so its value is key, and also we want it satisfies that the sum of the array is bounded above by the max sum. So if we transform the problem into such a statement, so this is a standard binary search pattern. So here the question is how to check if we can construct the valid length n array, right? Valid in the sense of these bullet items. So in one sentence, we can set the array at index to be key, and then we try to decrement the value by 1 recursively in both sides of the index. If the value is positive, we just set it as it is. Otherwise, we set the value to be 1. So once we set the values, actually we could easily compute the array sum, and then we just need to compare the computed sum S with the maximum sum. If S is less than or equal to the max sum, it's good. So it means that we can construct valid length n array. Otherwise, we cannot construct valid n array. So once we realize this point, then we can basically run a standard binary search paradigm. So here, in order to make it more clear, let's further elaborate the process. So here, let's assume we have an index 2 and n is 4. Let's first not specify the max sum. So if we have a 3 at index 2, right? So then this one here, none. So we can, because of this difference requirement, we can set it to be 2. The reason we set it to be smaller than this value is that we want the sum, the total sum later, is bounded by max sum. So we set this to be 2, and then we set this one to be 1, right? So here we decrement by 1, that's the 2. So we get such a array. So the sum is 8. For example, if you have a max sum that is 10, so this is the valid one. But if you have a max sum is that is 7. This is not a valid one, right? So here, if we have this one, this is 2, then we decrement by 1, so we're going to get 1. But we cannot further decrement because we already meet 1, and we need the numbers to be positive. Then we can set all the previous ones to be 1, right? Same for here. So here we set it to be 1, and if we still have further indices to the right, we need to set those indices to be 1. And in this example, the sum is 5. If you have a max sum that is 7, for example, so this is a valid one. And if you have a valid sum, maximum sum that is 4, this is not a valid one. Meaning that if I set this to be 2, this number is too large. I cannot construct a valid array. So this two paragraphs basically explains how to verify if given a value k at the index, can we construct a valid array, right? If that's possible, then we want to make the k as large as possible. So here is our plan. So first, I'm going to write a Boolean function to produce monotonicity. So this is needed for binary search, right? We need certain monotonicity. So here I'm going to call this function fulfill. So it accepts 4 arguments. So this I0 is the index. You can think of it as the index. N, it will be the length. And the max sum, as its name suggested, will be the upper bound for the sum of a valid array. So k is the value we are going to set at the index I0, right? So in plain English, this function checks if we could construct valid length n array with the value at index I0 to be k, and the sum is less than or equal to maximum. Then what the problem says or requires is to find the max k such that this function is true, right? Or just see, this is true. Then this k is a desired return. So here, before we write the code, let me make one more comment. It's actually easy to notice that given n and the max sum, if we set this element too large, then due to the absolute difference requirement for adjacent elements, then the array sum would be too large. Actually can exceed the maximum sum. That's why we want to find the largest possible, still making this fulfill function right. So if we have already digested the above thought process, writing the code is sort of routine. So first, I'm going to write the utility function to produce monotonicity. This basically is using a greedy method, or in a greedy manner. So here let's define fulfill. So it accepts k. We want to set the value at the index I0 to be k, and this is the length, and this is the max sum, right? So the return will be a Boolean, right? So the meaning is here, right? So now let's look at the function. So here basically we want to set that to be k, and then set the values, compute the sum, and then compare with the max sum. So here we need to play with the indexing, right? So let's first initialize the value at the very beginning 0, right? So we are going to compute the sum from the beginning up to index I0, and then we compute the sum from I0 up to the end of index. Then this way we compute twice the value at I0. Then we're going to decrement it by k after we add the two parts together. So let's look at the detail. First, if k is greater than I0, right? It's greater than or equal to 1. So this means that we can decrement to the left to set as k minus 1, k minus 2, up to k minus I0, right? In this case, the left part sum starting from index 0 up to index I0 will be, so this is the beginning one at index 0, and this is the one at index I0, and then we multiply the number of terms, that is I0 plus 1, and then we do integer division by 2, right? Otherwise, so if this is already non-positive, then we want to set some of them to be 1. So basically what we have is one part is from 1 to k, right? And then all the other terms is set to be 1. So from 1 to k, there are k terms, right? So let's first compute the sum of this part. That's 1 plus k times the number of terms, integer division by 2. Then from index 0 to n0, there are in total n0 plus 1 terms. And there are k terms set to be 1, 2, up to k. Then all the odd terms are set to be 1. So that's this part, n0 plus 1 minus k. So this is the left part, including the value at index n0. So similarly, we can compute the sum from n0 inclusive up to the end. So notice that to the right, how many terms? So the index will be n0 plus 1 and ending at n minus 1. So the number of items to the right of the index n0 will be n minus 1 minus n0 plus 1, then plus 1, right? So this number is nothing but n minus 1 minus n0. So now let's look at counting. First, if k is larger than this number of terms is greater than or equal to 1, it means that we can set the values of the right by recursively decrement the k value by 1. So at the end, index n minus 1 is still positive. In this case, the result or the sum of this part will be the last term, that is k n minus n0 minus 1. So then we're going to, so this is one term. So we're going to plus this one. This is the value at index n0. Then we're going to multiply the number of terms, that is n minus n0, right? So you can count like this. Left to the n0, there are n0 atoms. In total, we have n atoms. So to the right and including n0, we have n minus n0 terms. So then we divide by 2, right? Let's see. This is the first term, right? And this is the beginning term at n0. This is the term or the value we set at index n minus 1. Then times this one, integer division by 2. Otherwise, so we want to compute k terms to be value 1, 2, up to k, and the other terms are set to be 1. So the result will be something like this. So 1 plus k times k integer division by 2 plus, because we have n minus n0 terms in the right, and then there are k terms set to be 1 up to k, then other terms are set to be 1. So this block computes the sum from the beginning index up to index n0 inclusive, and this block computes the sum starting from index n0 to the end. So this way we use twice the value at index n0. Then we are going to do this one, minus k. So the final state of this result variable will be the sum of the array we construct on the air, right? So now we just need to return if the sum is bounded by max sum. If so, we see that if we set the value to be k at the index 0, we can do such a thing. Then the question is to be the second step. So we want to find max k such that this function is true. So here in the we want to use this one because this is the given index, right? So for above, we just need to use I0 for the convenience of writing. So now let's run the binary search. So the first step is to determine the search range. So low and high. So low will be at least 1 because we want all the numbers to be positive. The high will be the max value, right? So we're going to use max of none, or actually this would be better, max sum, right? So this one term will be already equal to the max sum, largest number sum allowed. And then we are going to do the shrinkage, right? So this is the search space or search range, and then the shrinkage. For the shrinkage, let's consider this. If low is less than high, strictly here, so we are going to do the shrinkage, because here we are going to I'm going to shrink from larger to smaller. The reason is that if it's too large, so this function will be false, right? So I'm going to do high minus low integer division by 2, right? So if fulfill, so I'm going to change this to be made, and the index is the argument to pass, and this n, right? And this max sum. If this is true, it means that we can construct valid array using this mid as a value. So in this case, we are going to set low to be mid. So notice that this way of writing, so at the value low, right, it always makes this function true. So otherwise, so if this is not true, it means that the mid is still too large. So we're going to set high to be mid minus 1. So here we set to be mid minus 1 because mid actually makes this function false, right? So this way we're going to return low at the very end, because low also always make this true. This is the full. This forms a full solution format to this problem. So now let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, that's about it for this video. So before we end the video, let me give a quick remark on the term complexity. So here, basically, the fulfill function is basically O1, right? Once you give me the k, n out, n, and the max sum, we can make a judgment. So the main term complexity is for the number of calls of this function. So because this is binary search, this will be logarithm 2 at this value, right? So let me comment here. Logarithm 2 of this max sum. Actually minus 1, right? So this, but up to a constant. So we can assume that the max sum is very large compared to 1. So this will be the term complexity overall. So with that said, that's the end of this video. Thank you.